Hello and welcome to the session. This session we will be talking about probability distribution function, commonly referred as PDF, and we will focus main on the probability density estimation. So last class we did have a overview on what is probability distribution function. Today's class we will just again repeat the concepts of probability distribution function. We will see how we can plot the PDF so that we can understand density estimation in a better way. So coming to probability density function, now this actually refers to a function that gives probability of all possible values of a random variable. So PDF basically tells how the probabilities are assigned to different possible values of a random variable. On the other side, cumulative distribution function or CDF represents the cumulative probability of a certain value of the random variable, and this we have seen in the last session itself. The different or the common probability distributions are Poisson distribution, binomial distribution, and uniform distribution. Now let's try to understand how we can plot the probability distribution function. As I said, probability distribution function, the goal here is to find the probability of occurrence of all possible values for a, let's say, a variable xi. So for this, let's take the concept of let's take a scenario where we'll imagine that the farmer wants to know the probability of an egg being a certain size. So on the x-axis in this curve, I have put the egg weight in ounces, and on the y-axis I put the frequency, that is the number of eggs. So what we can see here is the square boxes are nothing but the histogram distribution. What we can see here is the for the egg weight from for less than 1.5, the frequency is 5, and for the egg weight between 1.5 to 1.8, the frequency is 10 and 20. And for the weight between 1.8 to 2.0, you can see the highest frequency, that is 50. So that means, what is the frequency? The probability of an egg being that size, right? And again it reduces. So what we see here is there's a high probability of the egg being around 1.9, and there's a very low probability of the egg being around 2.1. Now how did I say this exact number is? We tried to plot the normal distribution, which I am shown in the blue line. So you can see that this histogram actually follows a normal distribution. So after I plotted the normal distribution, I am easily able to get the statistics of the number of x, right? Of the number of x which are of a particular size. So what we can note here is the probability distribution are basically idealized frequency distributions, you can say. Probability distributions are idealized frequency distributions. Now this is actually like a probability distribution function, right? Because you're getting the probability of the possible values for a particular variable. What is the probability of all possible values? So basically the frequency or the occurrence we are able to achieve, we are able to get through this function. Now once you have the probability distribution function, from that let's try to estimate the density estimation. So what is density estimation? It is a construction of an estimate based on an observed data of an underlying probability density function. So basically we are trying to construct an estimate of an observed data from the PDF. So density function is basically used for this case. What is density function? It is a density according to which a large population is distributed. So let's see how we can consider or construct a 3 density estimate. Let's take an example. Let's say we have taken we have done a survey of the number of people who are having diabetes in a particular age group. Okay, so based upon that data set or the survey, we are able to get 3 kinds of data. Okay, so what are the 3 kinds of data I am able to get is GLU, glue, conditional and not conditional. Glue means It's a case of the data set which I have got here. It's a case of plasma glucose concentration. Conditional means the in presence of diabetes, not conditional means not on diabetes. So based upon these three, I am able to construct three density estimates based upon the data set. So what are the three density estimates I am taking? Glue, conditional and not conditional. So this is what we observe here. Okay, see this blue dotted line is nothing but the blue dotted line, the high rise here which I see here, is actually the uh, estimated density of the probability of glucose when diabetes is present. Okay, so this blue mark is actually the estimated density of the probability of glucose when diabetes is 1. That's this one. Okay, probability of glucose when diabetes is equal to 1. So that means diabetes is present, and what is the amount of glucose given the condition diabetes is 1? That is this line. The green dotted line here shows the estimated density of probability of glucose. This is the density of estimated density of probability of glucose, and this red dotted line indicates the estimated density of probability of glucose when diabetes is 0. So what you can observe here is, right, this observation, it gives us that increased level of glucose is associated with diabetes. So this curve shows that increased, that is this blue line, increased level of glucose is associated with diabetes. Okay, so basically we are able to, based upon the probability density function, I am trying to construct an estimate. So what is that we have done here is, we have done here an estimate. So the y-axis here is nothing but an estimated density. So we have done an estimate based upon the observed data of an underlying PDF. Okay, so what is density estimation? It is a construction of an estimate based on the observed data of an underlying PDF. Fine. So with this, let's try to understand the formal definition of density estimation. So basically, where is it very useful in machine learning? Because we are in the course of machine learning, density estimation is a very important topic, especially when we are talking about unsupervised learning. Unsupervised learning, to recollect, we don't have labels here, we just have the data without labels. So most of the times here we will be doing classification based upon clustering. So density estimation is very important, very helpful in terms when we are using unsupervised learning. So some of the most commonly used or popular density estimation techniques are Gaussian mixture model, which we'll be studying, and KNN, very important neighbor based classification method, which we'll also be studying in the next sessions. So basically the formal definition of density estimation is, it is the problem of reconstructing the probability density function using a set of given data points. So that is what I tried to show in the previous example here. So what is density estimation? We are trying to reconstruct based upon the, based upon the PDF or the probability density function using a set of given data points. Or another definition is, density estimation is a statistical technique that aims to reconstruct the PDF for a random variable based on a set of observed data points. So that is in order to make you understand this definition, I gave you this example, which is actually not there in the textbook according to your syllabus, but the reason I gave this example was to make you understand this definition. So I hope this definition is now clear, where in the example I did show you how we can reconstruct the PDF for a random variable based on a set of observed data points. Now What is the goal of density estimation? The goal is to estimate the underlying probability distribution of a data set even when the true distribution is unknown. So you don't know the true distribution, you may not know the distribution of the data set, but still, just by having the probability, what is the probability, you can find out or estimate. So basically this is an estimate, that's why the word itself says density estimation. Okay, so basically we are estimating the density function. Okay, now what are the inputs for a density density estimation is we will be giving some data points, a set of observed data points like x1, x2, xn. That's what we did in the graph. In the example when I just started the session, we had some data points in the x-axis, and what was the output that we got? We got a density estimate of the PDF that generated the data. So this is what we did in the example. Now, coming to the mathematical way of mathematical definition of density estimation is, it is a probability, it is a problem of estimating the density function from an observed data. So let there be a set of observed values x1, x2 up 10, which is actually our input, from a larger set of data whose distribution is not known. So the estimated density function, let's call that as P of x. That's what we said in the example. P of glucose in presence of diabetes, P of glucose in absence of diabetes. That was the three density estimates we did. So basically P here is the estimated density function that can be used to value directly for any unknown data. So for any unknown data xi, I can find out the estimate. So in the example which I just started, xi was glue. For one case, it was glue in presence of diabetes, and it was glue in absence of diabetes. So it can be anything, right? So the density estimate, or P of xt, it has to be less than a particular value, let's say epsilon t. Then xt is not an outlier data. So suppose the estimate which I get is less than a epsilon t, then it is not an outlier data, or it is not an anomaly data, where epsilon would be helpful in specifying that whether this estimate is an outlier data or not. Outlier in the sense anomaly data, away from the different from the rest of the data. So there are two types of density estimation methods, parametric and non-parametric. Parametric density estimation is, this is also used, this of course this is a density estimation, and therefore it is used to estimate the probability distribution of a data set. But what is important here is the last line. We assume that the data follows a specific distribution with a set of parameters. Okay, so the main point in parametric density estimation is, we assume here that the data set which is the input will follow a specific distribution with a set of parameters. So let's see this example. Okay, so just like how we just saw the example in the beginning of the session, right? We had the histograms plotted, and from that we saw that this histogram for the egg case, right, for the size of the x which we just discussed in the beginning of the session. Suppose we will take the same example. The x-axis is the size of the x, and y-axis is the frequency. So let's say these are the x sizes, and we can see that the frequency or the probability of a number of x occurrence within that is increasing and then finally decreasing. So what you can observe here is, here also in this case, right, it follows the bell curve or the normal distribution curve. Suppose now you can easily see from that this is a normal distribution. So when you have a normal distribution, then it is following a specific distribution, right? The data set, this blue color is a data set, okay, which we've got some data x1, x2 up to xn, and from that data I am able to plot this histogram. And when I see the distribution, it is following a normal distribution. This red is what I estimated looking at the distribution. Okay, so the red is the normal distribution. So what you can observe from this graph is, here the data is following a specific distribution, which is normal distribution. Now since I know it is a normal distribution, as I've learned in the previous video, we can calculate the mean, we can calculate the standard deviation for this. So the next question is, why do we say parametric? Is because it is because of the relationship between the observations and its probabilities can be different based upon the parameters. Okay, so that's why we say parametric density estimation. Now, coming to the non-mathematical form of parametric density estimation, let's assume that the data is from a known probabilistic distribution. Let's say P of x in presence of theta, where theta is the parameter. And very good example of parametric density estimation is maximum likelihood function, which we will discuss in the next session itself. Okay, so maximum likelihood estimation is an example of parametric estimation. Now coming to the non-parametric, the difference is the last line. Okay, now this is also a statistical method. This is also a way of estimating the probability distribution for a data set, right, as we did in the example in the beginning of the session. But the difference is the data will not assume any specific parametric distribution. The data will not follow any specific parametric distribution. It will not follow any distribution like in the previous, unlike the previous example. It will not follow any bell curve. It will not follow any uniform distribution or a binomial distribution, right? So such cases we call it as non-parametric distribution. So probability distribution fiction, so non-parametric density estimation is a it happens in PDFs or probability density function that do not fit the random sample, or it does not follow a normal distribution. Example is, instead of one peak, it may have multiple peaks in the graph. So in such cases, I cannot calculate the mean, I cannot calculate the standard deviation. I will have to use a particular algorithm depending upon the distribution and find out the parameters. So that is why this is called as non-parametric density estimation. Okay, and very important concept. This is very important. Non-parametric density estimation approach is kernel density estimation. So the most common non-parametric approach is kernel density estimation. So what is kernel and all, we will see it in the next session. So coming to the what kind of techniques, right, we can use for density estimation is, we already saw that we can use histogram methods and we can use kernel density estimation methods. As I told you, now for non-parametric, if it is a non-parametric distribution, you will use a kernel density estimation method. So basically kernel is a function, and very good example of kernel is Gaussian function. So this is actually a Gaussian function which will also help to smoothen the data and estimate the PDF. So this you will understand. These concepts initially when I say you may not understand. As we go on into depths in this chapter, you will understand these things. And then one more is Gaussian mixture model. That is a very important technique where the data is generated from a mixture of simpler distributions and deep generative neural networks. Very important machine learning concept today. Everyone wants to learn this, where you can also use deep generative neural networks for density estimations, particularly in high dimensional spaces. So this is just for your extra information, just to know what are the common techniques you can use for density estimation. So in the next class, that was about density estimation today. The next section we will discuss about maximum likelihood estimation. Thank you so much, and any doubts please ask me in the comment box. Thank you so much, and please subscribe to the channel. Thank you.